Hello everyone, I'm very glad to present my project, Estimate Road Roughness using smartphone response data with a semi-supervised learning approach. My name is Leo, I'm a final year PhD student from Monash University, and I'm supervised by Dr. Yihai Fang. I'll be covering my talk in these 4 parts today. So here the image is showing you the pavement distress events. If we don't take good care of the pavement, it'll be turning into something that's more nasty. So $6.4 billion of vehicle damages was caused due to poor road roughness. And it's not just on pavement, it's not just on vehicles. Poor road roughness also attributes to 1/3 of traffic fatalities on road. Therefore, the monitoring or measuring of pavement condition has been a critical task. It's very important for us to know where the defects are so we can plan our maintenance works accordingly. When it comes to pavement roughness monitoring, conventionally, we have this professional survey vehicle, which has all the sensors to scan the pavements and obtain everything it wants to know. In the meanwhile, we can also rely on the public vehicles because we believe that the pavement condition can also be reflected on the dynamic motion of the vehicles that you and me drive. So when it comes to smart sensing, what we want to do is to engage both the survey vehicle as well as the public vehicles, with the help of crowdsourcing to ultimately improve the spatial and temporal coverage of our road monitoring network. But the problem is, how do we get the response data from the public vehicles? One way is to do it by using the vehicle-mounted smartphones, because our smartphones nowadays contains this RMSE sensor, which can be attached to the car, and when the car drives, it captures the motion of the vehicle body. But the problem is that the smartphone-based system is not designed, it's not a robust tool that is designed for this purpose. It's actually affected by many practical factors, including the vehicle's driving speed, the mounting configurations, and also the vehicle's type. So therefore, my main research question is, how is the smartphone system affected by those factors, and how do we improve the accuracy and the robustness of the smartphone system by leveraging those measurements that we take from the public? To answer this question, we've proposed this 2-module framework. In frame 1, what we do is to train a data-driven approach to estimate the IRI directly from the smartphone sensor outputs. Just as a note, the roughness index that we're talking about in this study is the International Roughness Index. That's being widely used globally to evaluate pavement conditions. And in module 2 is where we want to use a novel method to engage the public participants. So in the first module, develop a data-driven approach to estimate the IRI considering vehicle mounting and suspension variations. So when there's a road pavement, it could be driven by the survey vehicle, and the survey vehicle provides the label of our study. And in the meantime, it's also driven by the smartphone systems. And from the smartphone's road sensor outputs, we do feature engineering to extract the training features. The training features comes from like I said, smartphone's RMSE sensors. And for each axis of the triaxial RMSE motion sensor, we are looking at both time and frequency domains and calculate these statistical features. And these statistical features, along with the labels, will then be used as inputs and outputs to our multi-layer perception model, which we use to estimate the index. So this is our proposed architecture for our baseline model. In the next, I will show you some of the aspects on the data collection part. We develop our own app to collect the RMSE sensor as well as the GPS. We also ask the user to input their vehicle and the mounting informations, which we use in our model as categorical features. This app is installed to smartphones, which is mounted differently using different mounting configurations. And then these different mounting configurations were then deployed to vehicles of different types. As a result of this, we have a pool of data collected from different vehicle and mounting types. As for the experiment routes, we've selected 5 routes around our campus in Melbourne, Australia. And in the image on the left is showing you our ground truth survey vehicle. It has this profiler which scans the pavement, from which we can obtain the ground truth II, which is showing in the table. The table is showing you the ground truth II ranging from 0.5 to 6, which shows a wide spectrum of the pavement condition that we consider in this study, from good and bad pavements. As for the performance of our baseline model, we have achieved a R-square of 0.79. And for information, the R-square of the current commercial apps is around 0.73. And I do need to highlight that we are able to achieve this same performance when there's variations in vehicles and the mounting configurations. So that's module 1, where we already have trained the baseline model. In the next module, we're looking at how we can engage the public participants, or we name it adopt a semi-supervised learning to leverage the unlabelled samples that's collected from our public participants. If you look at our road network, essentially there are 2 parts. The first part is the road that we know the ground truth II for. We know the reference roughness, but in the meanwhile, we have a many road network that's never been scanned by the survey instruments, and in this road network, we don't know the ground truth II. When our public vehicles drive on these roads, essentially we have labeled and unlabeled samples. Most of the data-driven approach at the moment is completely based on labeled samples. That is, using fully supervised learning model. Whereas we believe there's a chance for us to explore those unlabeled samples, whether those unlabeled samples can also be used to enhance our model. Therefore, we propose using this semi-supervised learning-based algorithm. The one that we used in our study is called WIME, which stands for Value Imputation and the Mask Estimation Method. This is a off-the-shelf algorithm that was designed specifically for tabular data structure, which is what we have in our case. And this algorithm contains its 2 components, which includes learning from unlabeled samples and generating formal representations. And in the second component, it aims to train this predictor using representations of labeled samples. I'll dive into the details of this. So in the first components, what the algorithm is doing is to actually put a noise or change the value of the original features to obtain these corrupted features. And what we do is to train this encoder to reconstruct the original feature from the corrupted ones. As a result, we can transfer the raw features into their representations. And in the next components, we then use the encoder trained from the self-supervised learning to actually transform the feature of the label samples into their representations, which was then be used to train this roughness index predictor. So that's for the method or the methodology of the semi-supervised learning. Now the problem is, how do we get the data? As I said, we want to engage public participants. So in our study, we actually launched a data collection campaign where we are sending invites to graduate students in our university, to over 800 students. So what we have eventually was 15 participants. Then what they do is they install our app in their smartphones, and then they turn on our app on their driving trips to uni. So as a result, they're helping us collect the data on a daily basis. And here are some pictures showing you the in-cabin view of their smartphone and smartphone setups. So how does the semi-supervised learning algorithm help us eventually? As shown in this plotting here, we are using RMSE to indicate the performance of the models. Here I'm showing you 2 line charts, 2 lines. The blue one is the baseline model that we trained the first module. The second one is the semi-supervised learning algorithm trained model. So what we see first is there's a downward trend as we increase the label rates. The label rate here stands for the number of label samples versus the number of total training samples. We see there's a downward trend, at the same time, we also see that the line of the semi-supervised learning model is sitting below that of the baseline model, which is demonstrating this effectiveness in decreasing the RMSE or improving the model's performance marginally. And we would like to argue that this improved performance is not just solely attributed to more training data, but because by using this semi-supervised learning algorithm, we are able to learning these underlying patterns in these unlabeled samples, and then use that to improve the model's generalization ability on unseen data. That wraps up my presentation. I'd like to acknowledge that this research is supported by the National Transport Research Organization of Australia, as well as the Pavement Research Group and ARC. Thank you very much.